So in this one, we want to draw a free body diagram for a human that is falling freely from an airplane without a parachute. Okay, so let's draw our dot for our human, and then he is falling with a force due to gravity. There is no drag force. Okay, they said ignore drag. That means there's no air friction force. We just have a force due to gravity. So this is our entire free body diagram for this human falling from an airplane. He will probably die. Okay, now in this one, we have a skydiver, and he's falling downward through the air. So we draw our dot again. He is falling downward through the air. That's his FG at a constant velocity, which means that he's reached his terminal velocity, which means his drag must be equal to his gravitational force. And I tried to draw these arrows the same, but just in case, I'm going to go ahead and I'm going to write this next to it. And this lets anyone reading my diagram know that I meant these two to be the same size, even if they're not. Okay, so if someone, for example, was trying to grade your free body diagram, they would be able to grade it very easily because they would know that you meant these two to be the same. Okay, so in this one, we want to draw a free body diagram for an ant that climbs at a steady speed of up the side of his ant hill, which is inclined. So the first thing I'm going to do is I'm going to draw a little like plane right here. And it says that it's inclined 30 degrees from the vertical, which means we're going to go out 30 like this. Okay, and I'm going to, 30's kind of like this. And just to be clear, I'm going to go ahead and I'm going to write that this is 60 degrees. So everybody knows that that's 30. And that way, whoever's grading my diagram knows that I knew what I was doing, and I did my 30 degrees from the vertical, not from the horizontal. Okay, so now we have our ant. This is our ant. Okay, his gravitational force is straight down. That's not a very straight arrow, but it's straight down. Okay, his normal force goes off like this, perpendicular to that surface. Okay, so perpendicular to the side of his anthill. And now he's going at a steady speed, which means that his applied force and his frictional force are equal. So I can go ahead and I can write F applied equals F friction. And then my normal and my gravitational, they're not exactly equal, so I don't have to worry about that. Sometimes you can write like F, your friction force, plus your normal force is going to be greater or equal to your gravitational force, and that's what causes the ant not to slide down the anthill. But if you drew something like this, you would be good. And that one's kind of hard, and so but really just go ahead, break it down, draw your little diagram, draw your little dot for whatever your thing is, and then just go ahead and start putting forces in and kind of think about what could be acting on your ant. For this one, we want to have our crate is going to be accelerating across this surface. So I'm going to go ahead and draw my crate. Okay, I'm going to draw my applied force. Okay, I'm going to say that my velocity is in this direction. I'm going to draw a short frictional force. And then, don't forget, you have your gravity force. This is what causes your crate not to like float in the air. And you have a normal force. So when you do this, you want to draw, you want to write a couple things for your reader. You want to say the normal is equal to the gravity. And you want to say the friction force is less than the applied force. For this one, you want to go ahead, draw your horizontal surface. And then you want to draw your crate. And so this says that the cable is pulling the crate at a constant speed across the horizontal surface. So you have your F applied, and this is your applied force. And then you have your F friction. And these two should be about the same size. So I'm going to go ahead and write FF equals F applied. That way anybody looking at my diagram knows that I meant these two to be the same even if they're not exactly. And then since this ball is sitting on a surface, or this crate is sitting on a surface, there's a gravitational force. You always have that one. And that gravitational force is pushing downwards. And the normal force of the table, or the ground, is pushing up on the ball. And the normal force is always equal to the gravitational force. And that's what keeps this ball from falling through the floor, or the floor from pushing up on the ball. They're exactly even, and so there's no movement in the up and down direction. And I went ahead and I wrote these things over here, and so anybody that looks at my drawing knows that I meant these two to be the same, and I meant these two to be the same. They just may not look that way, and that's because I didn't use a ruler or anything to draw them, and that's okay.